Hi, this is Ferro who's speaking, and I'm very glad to present you this work titled Setup of a Numerical Model for Post Welding Heat Treatment Simulation of Steel Joints by Ferro, Meneghello and Berto. This is the summary of the work. Number 1, introduction and motivation. Number 2, materials and methods. Number 3, result and discussion. And finally, as always, the conclusions. Low-carbon structural steels, such as the S355, are characterized by good weldability and fine application in production of steel bridges, structures, ships, and so on. However, it is unfortunate that welding operation induce high residual stresses that reduce the fatigue life of those components in the high cycle regime. Different strategies were developed to face this issue, and when possible, post-welding heat treatment aimed at reducing the residual stress intensity could be a solution. In this scenario, prediction using numerical simulation of stress relief and deformation after post-welding heat treatment could be of great interest. But despite the great interest in models related to post-welding heat treatment simulation, in view of the prediction of a fatigue strength improvement coming from stress relief, not sufficient literature was found in this topic, and in particular when the common structural steel S355 is considered. Therefore, this work is aimed at filling this gap. Square groove T-joints were obtained by arc welding a 5 mm thick web on a 5 mm thick flange made out of S355 steel using a single pass on only one side, as shown in the figure on the left side. Before welding, the flange and the web were tack welded and perfectly positioned perpendicularly to each other using a square. See the figure on the right side. More in detail, manual gas metal arc welding was used to produce the samples, and parameters are summarized in this table. After welding, the joints were heat treated at 510 Celsius degree for 3 hours. The measurement of the joints distortions before and after the stress relief heat treatment was performed using an absolute arm and a support to keep the sample in position during the measurements. The obtained points cloud was then elaborated via software to obtain the angle between the web and the flange. The welding simulation was carried out according to computational welding mechanics strategy. The mesh of the model is shown in this figure on the left. In order to take into account the effect of filler metal, a group of elements shown in blue modeling the throat was created. Thermometallurgical and mechanical properties of both filler metal and parent metal were taken into account by using a SysWeld database. The heat source was modeled using a double ellipsoid power density distribution function proposed by Goldak, where its parameters are calibrated by using experiments. Radiative heat loss using the Stefan Boltzmann law and convective heat loss were applied at the boundary of the plates to be joined. In the mechanical computation, the weldment was considered isostatically clamped. After welding simulation, the joint underwent the furnace thermal history used to carry out the experimental stress relief heat treatment, as you can see in the figure on the left. In the mechanical computation, the viscose plastic deformation of the alloy was modeled by using the creep law written in the right side of this slide, where alpha is the kinematic strain hardening variable and H, K, C, and P and N are temperature dependent parameters. The figure on the left shows some thermal results. In red, you can see the fusion zone shape and dimension that was found in sufficient good agreement with that obtained in the experiments. In the figure on the right side, numerical result of binite proportion after welding is shown. In blue are zones characterized by a fully ferritic microstructure. The fusion zone microstructure consists of acicular and Widmanstatten ferrite with island of alloteromorphic ferrite, in agreement with the microstructure observed in low-carbon steel welded joints. The heat-affected zone, on the other hand, was mainly composed of binite as predicted by the model. After welding, the angle between the flange and the web obtained by the numerical model was 88.8 against an experimental value of 88.56 that is considered a reasonable good result. After stress relief heat treatment, the distortion angle didn't show any variation, and the numerical results confirmed that experimental evidence. However, residual stress reduced significantly as shown in this figure. So we arrived to the conclusion. Number 1, a setup of a numerical model aimed at predicting the deformation and residual stress before and after post-welding heat treatment of structural steels was successfully carried out. Number 2, the main phenomena involved in the welding process and heat treatment were taken into account with particular attention to solid-state phase transformation effects. Number 3, a creep cinematic law was implemented and applied to predict the mechanical effects of the stress relief heat treatment. Number 4, results showed a good agreement between the numerical and experimental results in terms of both microstructure and welding-induced distortions. Finally, number 5, further investigations are in progress to validate also the residual stress relief prediction. Well, hope you enjoyed this presentation. These are my contacts, and I hope to see you soon. Thank you for your kind attention. Bye bye.